Thanks for coming. I'm Jackie. This is Louise. We're from the Open Source Robotics Foundation. We're going to introduce our organization and tell you all about what we do. And hopefully there'll be some interesting C++ tidbits here, but mostly we're going to talk about how cool robotics is and how cool robotic simulation is, as you probably all already know. Does this thing work? There we go. So OSRF, or the Open Source Robotics Foundation, is a small nonprofit dedicated to making the robot revolution also open source. We're 17 people who are all pictured on this slide, based in the San Francisco Bay Area. And we're mostly software engineers, and we work primarily in C++. Our two main projects are ROS, or Robot Operating System, and Gazebo, which is a physics simulator for robotics research. So I'm going to spend the first half of the talk introducing ROS, and Louise will talk about Gazebo, and we'll take all of your questions at the end. Although if there's something unclear on a slide, you need clarification, just raise your hand. So this is all, talking is boring, so we'll watch some cool robot videos for a while. Cool, so this video says 5 years of ROS, but actually ROS is an 8-year-old project, so it's 3 years old. But hopefully it'll give you some idea of the kinds of robots that run our software. So ROS is a framework. It's a collection of a unified communication protocol with a simple message interface for passing messages between processes, but also between devices over Ethernet or Wi-Fi. It's also a set of tools for introspection, orchestration. It's a CMake-based build toolchain for coordinating many packages, because there's a lot of software that goes into making a robot do really cool stuff. It's also an ecosystem of high-level packages. Thanks, John. It's an ecosystem of high-level packages for motion planning, navigation, computer vision, really complex research tasks that roboticists need to solve. And it's a really awesome community of researchers and industry professionals who are trying to do things with autonomous systems. So I think YouTube is taking over this. In summary, ROS is network plumbing, tools, capabilities, and an ecosystem. I'm mostly going to talk about the first two aspects at this talk today. But to make that broad overview more concrete, here are some statistics. Most people at this conference might not know about it in a general software engineering context, but most people in robotics have heard of it or are using it, particularly in academia where open source tools are really valuable. My favorite statistic on this slide is that this is Robonaut, which is a robot made by NASA that's currently running ROS on the International Space Station. It's the farthest away from Earth that we've gotten. And this hopefully is useful. It's kind of hard to see the text, but this green section is the percentage of C++ lines of code, comments are ignored, in our code base. So this is the desktop full Debian package, and it has basically all of the core things you need to make a robot go, and some stuff on top of that. So Python comes in a close second, and there's XML, YAML, also CMake and C, so that's all in the same family. That's why we're here. So I'm going to tell you all the story of how a ROS message goes from point to point. So let's say you have your laptop, and you have a Turtlebot, which is one of the first robots that was running our software. And basically, all it does is move with 2 wheels and collect data, and it's cool Xbox Connect. So you want to write a program that makes the robot move. So you're writing in C++ because you're a C++ developer. You make a twist shared pointer to a twist message. A twist is a linear and angular velocity. So this is a boost shared pointer because we're in ROS 1. And you do some other stuff to initialize this publisher and the ROS context. And you just call publish on your message object. It's very simple. So because you're publishing from your laptop, we're going to call it the publisher node. The message is going to get serialized and published over this topic, which you specify when you construct the publisher object. and it's going to be sent over the internet into the cloud. For those of you who want more details, it's a TCP-based transport, TCP/IP. There's a layer we call TCP/ROS that converts your C++ struct into a message packet. It goes down the pipeline, back over to this topic, which your Turtlebot, the subscriber, is listening on via TCP sockets. Oops. Spoilers. So message gets deserialized. You enter the subscriber callback, and then the Turtlebot is running software that was written by someone else somewhere far away, but it's available on the internet, open source. It enters the callback, and then it probably calls really low-level motor drivers that were written in C to interface with the motors and make the thing move. So yay, we've accomplished everything we need to, right? Really simple. So I've given you a really high-level overview of what ROS is. But in this talk, I'm actually going to focus on ROS 2, which is the project that I work on primarily. And ROS 2 is basically, it's kind of like the Python 2 to Python 3 migration effort. It is an API change and a major overhaul of the code base to kind of modernize this 8-year-old project for the new era, and for many different areas in robotics that have developed since the ROS project was initially developed for academia. So there's a couple of capabilities we're focusing on. This lists 3 major ones. We want to be able to run ROS natively on embedded systems with minimal OS or no OS in a bare metal situation. We want to make ROS configurable to run in real time, which I'm going to focus a lot on that aspect of ROS 2 today. And we also want ROS to be able to be performant in high traffic situations with many robots. And because currently, with a data protocol built on TCP, it tends to degrade in a really low, high traffic situation. And it's kind of hard to picture this, but we want to modernize the API to C++11. Originally, we relied a lot on Boost for things like shared pointers, which is exactly what the people at this conference want us all to do, which is great. So again, going into a little more detail, instead of using TCP for transport, we're switching over to DDS, which was originally designed for, keep misclicking, the Internet of Things and robotics and autonomous systems. There was actually another DDS talk on Monday, which is really good. We're also planning to target the 3 major operating systems pictured here. ROS 1 really reliably only works on Linux. There's pretty good support for OS X, but maybe not all features are there. In Windows, it's like almost unheard of to have ROS running on Windows. Again, we want C++11 and Python 3, but not so relevant to this conference. And we haven't done a lot of work yet in ROS 2 and Python. Currently, ROS 2 is an alpha. Projector died. OK. So ROS 2 is an alpha. We made our first alpha release last month. So this is all kind of presenting to you from a working prototype that still has a long way to go. To give you an idea of the API changes between ROS 1 and ROS 2, ROS 1 is going to be on the left, ROS 2 is on the right, and this is a simple subscriber. So you might not see a lot of differences, and that's actually sort of intentional to ease the migration effort for our users, but there are also, again, major changes in what we're exposing. The first is a really small thing, but this bothered me. There's a type def in ROS 1 for a boost shared pointer. Here it's a shared pointer of a const message. And this was type def to just a pointer. So a shared pointer was just a pointer. And in ROS 2, it's actually called a shared pointer. That really bothered me because it's conflating pointers and shared pointers, which could lead to really mistakes. So in this line, ROS init, argc argv listener, we're initializing the ROS context, and we're passing the name of the node. Remember, our node in the example was our laptop. Really, it's a process running on your laptop, running this code. So you pass the name of the node, and you create a node handle, which is how you access the ROS context, basically. In ROS2, you call init, but you don't pass the name of the node, and you create a node object with the name. So this, basically, you can have multiple nodes in ROS2, and you couldn't in ROS1. Nodes mapped directly to processes, which is a big limitation. If you say let's say you compile several shared libraries with different nodes, and you want them to run in the same process in one situation, or maybe you want to run them in different processes, this architecture gives you more freedom. The subscriber initialization is conceptually really similar. There's some slight different syntax, but we're using auto, and we have to specify the template here. If we didn't specify auto, it needs to infer the type from this template, but mostly the same. Then you call spin in ROS1. Spin is essentially a blocking call where you enter the event loop, where you can, once you're blocking in spin, you can receive the callback from the subscriber, which here is called chatter callback. In ROS2, there's a similar call that's just spin without any objects passed to it, but there's an alternative, which is you can instantiate an executor. And so we're exposing the executor to the user. The executor is just something that listens for all the DDS communication and gets the work that's going to come in on the network or via IPC, execute it in a fashion that's specified by the user. So you can specify a threading model, which is also different from ROS1. And you can add nodes arbitrarily, add and remove nodes to the executor. And the executor is going to listen for work to be done by that node, or done for that node. And then you call spin as a class function of the executor. So a more high-level overview of the ROS2 architecture. We're placing a lot of emphasis on this hourglass pattern here. We want users to be able to write code in many different languages. So we have different client libraries, which they're going to access, having the kind of API that you saw in that last slide. But these client libraries, the implementation in some form or another, I'll call the Unified ROS Middleware API, which is this abstract wrapper over the many DDS implementations. So is anyone in this room really familiar with DDS? Cool. So there are many different implementations of DDS. None or maybe one of them is actually open source. There's an upcoming one that we're actually supporting in this effort. So for someone who already has a DDS license, they can use OpenSplice, maybe new open source implementation of DDS or RTPS is here. But those details are all hidden to the user and actually to the client library. So I'm going to now shift gears a little bit and talk about aspects of ROS2 development that I find really interesting, and I hope you do too. So one thing I've worked a lot on is real-time support in ROS2, prototyping what that's going to look like. So who in this room knows exactly what I mean when I say real-time system? Raise your hand. OK, so that's like most people. But actually, the real-time and low-latency SG14 is happening like right now. So all the experts are probably in that meeting. So including, not an expert, but familiar, right? So real-time computing, essentially, you have deadlines. You have to stick to your deadlines. If you don't stick to your deadlines, that's really bad. That's an error. So you have some update rate. Here it's, that line. And you have some acceptable error, which is often called your jitter. So you can't block for longer than the deadline plus your error. And if you go over it, it's often called overrun. So let's say in this loop, you're getting data, and you block so long that the call where you get the data is past your deadline, then that could be bad. So in some cases, you throw an exception and you exit. In other cases, maybe you just throw out that data and ignore it. Even fancier, you might adjust quality of service settings so you get more data in the future. But that's essentially the definition. And you might ask why we care in robotics, but I think the question is actually why don't we care? Real-time reaction is really important when you're reacting with the real world on a real timeline. So if you don't have real-time performance, then your humanoid robot is going to fall down on the steps and break itself. Your autonomous satellite is going to react poorly to old sensor data, and it's going to maybe go out of orbit. And your autonomous car is going to think the pedestrian that it saw is no longer there, or maybe not see a pedestrian and then kill it. So roboticists really want real-time computing, and many of them don't have it because many roboticists are researchers who don't know how to write real-time safe code. So in order to deliver ROS2, a framework all roboticists can use that's real-time safe, all layers of this stack must be configurable to be real-time safe. Maybe not Python, maybe we can just ignore that, but the user code that they provide, the client libraries we provide, the ROS middleware API we provide, the DDS implementation someone else is providing, and the operating system they're running their code on. None of those places can have a thread that blocks past the deadline. So how do we achieve this? Well, commonly, people who are familiar with real-time computing probably know that when you, the default heap allocator for basically any platform is not real-time safe. You could end up blocking non-deterministically while you're waiting for, or you're looking for a free block of memory. Or maybe, let's say you're looking for a free block of memory because you're allocating on the heap, and you have to go to main memory because you're swapping out memory that's in RAM. And that could take a really long time, and that means you could miss a deadline if you call new. Or again, if you're returning memory, then that's also incurring those same costs. So I looked a little bit at how we were going to make memory allocation real-time safe in ROS2. A lot of people in real-time computing say you can have kind of this stage where you pre-allocate memory. That's not real-time safe. And then you have your critical section where you're running that update loop that's on a regular deadline. And that has to be real-time safe. Then once you exit that loop, you deallocate the memory like a responsible person. And you have your non-real-time safe cleanup section down here. So I mapped that to executor spin as the real-time safe section. You enter this update loop. You're just going and going, getting jobs you need to do. And at the end, you clean up all the memory that you allocated at the start, analogous to our example where we created the subscriber and the node handle and all that. So this is kind of going into a little more detail of what spin is going to look like. It's really straightforward. We have this RMW wait call and RMW middleware interface. We're talking to DDS. DDS is actually going to take care of blocking for us because DDS claims to be real-time safe, the specification, so we'll just rely on that. We're going to create a DDS wait set. We're going to make that block until work comes in on the network. If there's work available, we'll wake up. Even if work is not available, we'll wake up when there's a timeout so we can get our deadline and tell the user no data came in. So one thing here is when we tried to pre-allocate all the memory, you need to allocate for the representation of work that's going to come in after you wait. You don't know what work is going to come in, so you need to dynamically allocate that. And in the initial implementation of this, we dynamically allocated, a subscription comes in. We have the representation of that with the metadata, the job that needs to be done. A client came in, client callback. Similar thing for that. But we just can't call new in this context. So I prototyped this architecture, basically, where we have different kinds of memory strategies, and you pass that to the constructor of the executor. So by default, when we need to create a handle to this representation of the object in RCL CPP after we wait, we just call new malloc and free here, new and delete. Not the same thing, but heap allocation. If we're in a real-time safe situation, you can pass a different memory strategy, which inherits from the same base class as this, which refers to pre-allocated memory pools. So the executor code is all the same, general, dependency injection. It's great. But you might ask, why don't we just use this? Because it's more real-time safe. Why do we have to worry about this whole scheme, flowchart, crazy? Well, the drawback here is that you need to know in advance the maximum number of those executables that I said before you allocate this memory in the constructor. So what's nice about this, because it's dynamic, you just say new, like 5 subscribers, new whatever subscribers. It's great. But here, if you go over 5 subscribers, whatever your maximum number is, you throw an exception because you don't have enough memory to store those subscribers. So there's benefits and drawbacks of both. And one of the challenges making this framework is meeting the needs of users who want more simplicity, users who want more configurability. But I think this works pretty well. So, but does it really work pretty well? I don't know. Let's do some benchmarking. So I set up an example where, so it's very simple inverted pendulum simulator. An inverted pendulum is just a mass on a stick that has a motor at the bottom. And the motor is trying to balance the mass that's swinging on a stick. So it's all in simulation, though. And this is kind of the software topology of the nodes that are involved in this simulation. We actually have one process that is a simulator creating the physics data, and then it's also simulating a sensor on the motor, and it's publishing to a controller. So in a real situation, the controller might be a computer, actually, that's running controller code, like a microprocessor. The simulator node, this might actually just be a sensor node. And these might be connected via Ethernet on your board on like a robot that's running here. So it publishes sensor data, and it also sends a command. And here it just sends it to the simulator so the simulator can move the pendulum. And then we have non-real-time processes that are doing non-real-time safe actions, like logging data that's being published out of the controller in a file and printing it to the screen. And we also have a non-real-time process that publishes to the simulator by basically taking key input, saying, what is the theta I want to command on this pendulum? So some other really technical details. The default Linux scheduler is not real-time safe, so I used RT preempt, which allows for full preemption of the scheduler. I used pthreads because the C++11 thread interface doesn't expose thread priority with round-robin scheduler, but FIFO I think is also a valid option. This is actually deprecated now, malloc, but basically it's a way to write your own custom malloc, right? So I wrote a custom malloc that just said, hey, you're mallocing, and if it was after calling spin, then my test failed. Luckily, that didn't happen. And also, get our usage counts page faults, page faults are bad for real time. I'm not going to go into too much detail again here. If anyone wants to know more about page faults, just ask me. And so the goal, this is kind of a gold standard in robotics, is a 1 kilohertz update loop. And that's basically, if your computer is updating every millisecond, you're basically running faster than your motors can react. So that's really good, because your motors can't react faster than you are and do something unexpected that you don't know about. And we want a pretty small margin of error. 3%, again, is, I don't know who comes up with these numbers, but it's a gold standard that roboticists use. So the results look pretty good. I ran the example for a little over 2 hours, and the average is very far below what we wanted. So this percentage column is probably more useful to you. The average is very far below our, this by the way is jitter, not like the amount of time it took in the update loop. So this is like the error here. Very low error, but our maximum jitter is actually a little bit over 3%, by 0.5%. And our minimum is, again, very low. But our histogram here shows that it's kind of a bimodal distribution, like the error that usually, the jitter that usually came in, and it's very, very low. But we also have, you can't see in this plot, but we go over at around 35,000 nanoseconds or 35 microseconds. And this is marking our maximum allowable jitter if we want to stick by real-time requirements. So yeah, but in conclusion, I think this is a really good start. I learned a lot by setting up this prototype, but we've got a really long way to go, especially because there's features like client-server communication, which I didn't really talk about, that are not real-time safe right now and just block. They use standard features. It's like not great. I'm not using standard allocator anywhere, which I think is the next step for creating real-time safe memory allocation for standard library structures by providing a pre-allocated pool to vector and map instead of just like calling new and they resize, which is what they do by default. And also, lock-free programming. I went to some cool talks about this at this conference. Maybe I'll prototype them. I don't know. Yeah, so real-time performance is actually really important on microcontrollers, which are cool. I'm not going to talk much about microcontrollers, sorry, but maybe in a year I'll know a lot more about them. But there are also all these desktop platforms we're trying to support. And I'm really happy to report that we have stable CI jobs for all three of these. We could always improve our test coverage, but it's cool. We can prove that ROS2 does actually work on Windows, unlike ROS1. But there are a couple of caveats to that. Actually, the ROS team at OSRF is a very Linux-focused group. We're all Linux developers by training, and so when venturing into Windows development was really an adventure for us, because there are some things that Visual Studios doesn't like. Visual Studios 2015 doesn't like that Clang and GCC really don't have a problem with and don't even warn you about. So I don't know what's up with that. So I'm going to just give an example of that. So we wanted to do this, and this is essentially, we're creating a service that's another communication primitive in ROS. And it has a function callback, a function pointer that you pass to it, and a name. That's less important. And the function has type request and response. Those are messages. Well, there's another option, though. You can have a name and a callback that takes a request ID. That's metadata. You don't need to worry about too much what it is, but it's a struct, and then the request message and the response message. So we had these two template types, and we implemented them. But calling the function compiled on these two platforms, but not Windows. That seems weird. It basically said this call is ambiguous. So we would think the compiler would be able to resolve the template overload because it's given a request message and a response message. It's clear that it's this implementation of the template, or this declaration of the template, not this one. It turns out the standard function implementation on Windows Visual Studios, it's greedy, and it basically just goes with the first template declaration rather than overloading these two, which it's an incomplete implementation of the spec. So we had a workaround with more insane template stuff. I don't know, this stuff is crazy. And this is actually just a very small excerpt of it. So we basically have standard enable if that says, only compile this function or only overload this template if the arguments have the right type. So we have function traits, and the argument is going to be response. And we had one for, argument 0 should be the header, argument 1 should be the request, argument 2 should be the response. Then we had another one that was just like this with the other function signature. This is kind of crazy, yeah. But this also didn't compile on Windows. It compiled on OS X and Linux, but not Windows. So, our workaround totally didn't work. We throw up our hands. Turns out we did some research. Actually, luckily, I wasn't the one who was working on this. It was someone else on my team who I feel really bad for. And this is a link to the blog post explaining, yes, expression substitution failure is not an error, which is what I've been demonstrating here. Not overloading template types is not fully implemented in Windows. So we ended up doing this. Static assert, still, pretty good. You can catch this at compile time, which is good. But it's less efficient because rather we get to the static assert and we're not skipping over the function at compile time. Okay, So that was kind of crazy, but that was the deep dive into ROS2 technical details. So, this wraps up the ROS portion of the talk. You now know everything you need to write robot software, right? You can just go online and download our software for free. It's really great. But you need this. You need a robot. And robots that are interesting with arms and sensors are really, really expensive. And so unless you're at a company that can just afford to buy you one, or you're at a research lab that does robotics, then you probably need an alternative. And so why not try a free simulation?
Cool. So I'm going to talk about a robotic simulator where you can do this kind of stuff called Gazebo. It's also maintained by the Open Source Robotics Foundation. Let's show you some videos about what Gazebo can do. So you can simulate a wide variety of robots, as you're going to see here in this video. And the question is, well, why would you need a robotic simulator besides the fact that you might not have the robot? Well, even if you have the robot, you might want to just try things in simulation because it's faster. You can iterate faster. You can try to different algorithms that if you put in the real robot, you might break it, or it might be too troublesome to go and turn on the robot, and if it falls, you have to put it back up. So you can go through these things in simulation and do research on your new algorithms very much faster if you're simulating it. Another reason to use simulation is for prototyping. You don't have a robot yet, and you're thinking about it, you do it in simulation, tweak it a little bit, and then you go for the physical prototypes after doing simulator prototypes. And simulators are also widely used in competition, so it's good to have a controlled environment for all the competitors. And some of the scenes here are from actually the DARPA Robotics Challenge, which was a big robotics competition that happened along 3 years and just ended this year. And the first stage of the competition was to compete inside simulation, and Gazebo was the official simulator for that. So all the teams had to compete against each other just with their algorithms. They didn't need to have the robot. Everybody was using the same robot inside simulation. And the best teams were actually paid. They received a robot in the end to compete in the real world, like physical reality competition. So you can see that Gazebo has a lot of features. You can interact with hardware and things like this. So that's a little intro to Gazebo. Let's check out some stats. So right now we're on version 6, but actually Gazebo is like quite old. It's been around since 2002, so it's like 13, 14 years old right now. And we have right now about 1,000 downloads a month. It's a lot of lines of code, over to 50K, lots of comments too. Function coverage is not as good as we would want, and this is something we're working on improving right now to make it more robust. And we have about 60 plus contributors from all around the world contributing back to Gazebo. Just for you to know, what's happening? Okay. Spoilers, no. So what's involved in a robotic simulator? You can see that there is a lot going on there. Most people look at simulators and they think it's just a video game with crappy graphics and very good physics. And it's basically that. So here's like some of the dependencies we have. So these 4 here, Open Dynamics Engine, Bullet, Dart, and SimBody are the 4 physics engines that we support in Gazebo. So you can change that in runtime. You can choose if your simulation is more about soft bodies, you might want to use one of them. If you need some features from different physics engines, you can change that in runtime. So it all comes when you have to compile Gazebo with them, and then you can just use them. For rendering, we use OGRE. And the rendering is not only used for you to see your robot doing things, but also to generate sensor data. So the robot has cameras in it, and you have to generate the vision for that camera. We use OGRE for that too. We use Qt for the graphical interface. We're still using Qt 4. We haven't transitioned to 5 yet. We use protobuf for the message passing between processes, for the message description. We use Boost for a bunch of things. So as you can see, Gazebo is a quite old project, and we're adapting to new technologies slowly. We are, since Gazebo 5 you can use C++11, but we're not making use of all the features of C++11 yet. So boost shared pointers is something, for example, that we still use, but we are adapting little by little. SD format is the XML format that we use to describe the world. So everything that the user wants to have in their world in simulator, in the simulation, is described in XML. So you have like a world tag, you have text for robot models, for all the physical properties, for the visual description of the robot. So everything is described in the SD format. And Ignition is a project that we're starting to break Gazebo apart. So Gazebo has a lot of libraries inside itself, and it's becoming a very big project. So we're trying to take things out. For example, our math library, we're separating it out of Gazebo, and we're making it into an Ignition library, and just to make Gazebo itself a little bit lighter. So I thought I would talk about plugins today because you can see some of the C++ code that users can have to write to interact with the simulation. That's the way that you control your robots, you control your worlds inside the simulation. It's all writing C++ code. And I thought it would be fun to make a plugin to explain the plugins. So let's go into Gazebo and hope everything goes okay. It's sort of a demo / presentation. Let's see. Okay, we're inside Gazebo. Wow. This is our simulated world here. Usually, it would be much more interesting if you're doing some robotics stuff, like you would have some fancy robots in there. But right now, I just like put some slides there for us to look at them. So let's start with the plugins. Plugins are the way that users interact with the simulation. They have to write C++ code. And another way that users can interact with the simulation is through ROS, actually. You can, but that is done by plugins in the backend. But for many users who are using Gazebo, they are just writing ROS code. And that's the same code that runs in their real robot and in the simulator robot. And many times they might be writing that in MATLAB or Python or whatever they want. But the bridge is done in C++. So let's take a look at our plugin structure in the architecture in Gazebo. So we offer a C++ API for users, and which is basically our whole code base. So it's very flexible. You can do pretty much anything inside the simulation, but it's also very dangerous because you can break Gazebo if you want. And it's been done like this historically because originally Gazebo was widely used by researchers who were very tech savvy. They knew what they were doing, and they wanted to have full control. They would even write their own simulator if they had the time, but they were using Gazebo for convenience. So they wanted the freedom, and they have the freedom to do whatever they want with the simulation. But more and more Gazebo is being used by people who don't know how to write C++ code so well, like mechanical engineers like myself, or like high school students. So we are trying to make the API easier and the entry points into Gazebo simpler and more straight to the point for people who don't want to deal with all the details of the simulation. So we're offering the C++ API. Which I'm going to talk about. It's also worth pointing out that since it's the whole code base, user code is very similar to developer code. So in a way, it's very easy for you to go from a user to a Gazebo developer because you kind of know the API and you're like, oh, I want to fix this in Gazebo. And you just like, OK, let's make a pull request to the original application. So the way that users have to compile their code into a shared library. And there are a few ways that they can refer to that library inside Gazebo for Gazebo to find it. So you can either use the SDF, the XML format that I talked about earlier. There is a plugin tag. You just put the name of your shared library there, the .iso file, and Gazebo is going to find it for you. You can also just do it by the command line. There's an argument. And for GUI plugins, for example, you can put it in a GUI.ini file, which is going to be loaded every time you open Gazebo. So if you want to add your own buttons and stuff, I'm going to talk about each specific plugin in more detail later. So you just, for Gazebo to find the plugin that you referenced by the file name, you just have to set this environment variable called Gazebo plugin path. And that's pretty much it. It might be simple for this for this audience, but for people coming from mechanics and all, it's like, what's an environment variable? Why do I have to do this? So it's as simple as we have made it so far, and we're trying to make it even simpler for people. So we offer a wide variety of plugin types that you can write, and I'm going to talk about them later, but they all have a very similar structure, which is there's a load method that you have to override. And that's your entry point, and from there you can add your callbacks, you can do whatever else you want, but they have this thing in common, which is the load method. There's also like a couple of other methods like init and reset that you can also overload if you want some different behavior, but load is the bare minimum that you need. And the way that plugins communicate with the main application and with each other is by shared pointers, so they can have access to shared pointers via the load method. They receive some shared pointers, and there are also some global functions that you can access some of these pointers. You can use events for communication inside the same process and messages for inter-process communication between plugins and the simulation. So this is an example of a base class. This is the model plugin base class, but all of the plugin base classes have very similar structure. So you can see it's very simple, just the model plugin here. There's a constructor, a destructor, and the load method, which is pure virtual. And you receive a model pointer, which is a shared pointer, boost shared pointer, and you receive an SDF pointer. The model pointer gives you access to when we say model in Gazebo, we're referring to the robot. The robot is a model, which is a collection of links and joints all in one. So that unity that makes up something like a robot or a table. They are both robot models. And SDF is how you're going to pass in parameters to this plugin. So remember I said the plugin, there is a tag in XML that you can specify the plugin. You can also specify tags inside that tag, and you receive all that structure here, so you can deal with it in your load method in any way you want. So you don't need to compile to change the inputs. And there is this very helpful macro to just register the plugin with the simulator. So this in the backend calls DL load and dynamically links the library with the simulator, but the user only sees this and just calls this, changing here the type of plugin. This case is also a model plugin. So these are the plugin types we offer right now. I'm going to go over this list very quickly and why you would want to use each one of them. A road plugin is sort of a God's view. So you have access to all the model pointers in the world, all the lights, you have access to the physics engine. So you would, if you want to change the physics engine dynamically, you would want a road plugin. If you want to measure how two robots are close to each other, you would want a road plugin because you would have access to both of them. So that's a road plugin. A model plugin is more something inside the robot or any other model. So you can use it, for example, for a joint controller. So you have access to the pointers of all the links in the robot and all the joints. Or also for physical phenomena. For example, Gazebo comes with a lot of plugins that you can use, like pre-made plugins. And one of the model plugins we offer is a lift drag plugin. In the videos, you saw an airplane flying, and that's running a model plugin that is applying forces to the plane according to its velocity and all. So that's all done with a plugin. It's not even in the physics engine. Like the physics engine is running in the back end, but you call the physics engine, like, apply force to this, and then it takes care of the rest. Sensor plugins are, for example, you have a camera sensor and you want to filter that data or modify it somehow, so you would have a sensor plugin. Visual plugins are for like the rendering part, so you can have dynamic textures and interact with everything that you're seeing. System plugins are the ones that are the most powerful. They're loaded, even before Gazebo is loaded, they have access to the command line arguments, so they can modify anything that is going to come afterwards. So this is like for the experts, for people who really know what they're doing and they really want to have full control, they would use this. And GUI is, I'm running a GUI plugin right now. Right now I'm running two plugins in this in the simulation. One is the GUI plugin that I'm using to get key events and pass the slides. And the other one, I don't know if you saw a drone flying around, that's a model plugin. And I'm going to explain these two plugins for you now. So first one, let's look at the model plugin that is running in the drone. I try to keep the physics to a minimum. I think people in this conference are not very interested in the physical details of what's going on. So I just kind of cheated the physics, and I made an animation with the drone that is flying around. It's just very simple. I'm setting keyframes. I have a list of positions in the road that the drone has to go to. I pass that as in the XML, and the plugin just loads that XML, creates an animation, and runs in a loop. So I tried to keep the example in one slide. I think I was able to fit it. So we start with registering the model plugin up there. Then we subclass the model plugin class. We're calling this the animate model. And then this is the load method. We're receiving the model pointer, which is a pointer to the oh, there it is. To the quadcopter. And we receive an SDF, which is loading that road file with all the poses that we want for the drone. So here we start going through that file and generating a keyframe here for each one of those poses. And in the end, we just set the animation for the model. Since I set this here to true, it's going to loop forever. So that's it. This is very simple. You probably wouldn't want to use too much animation in your real simulations because that's cheating. The drone is like not going to respect physics at all. If wind comes, it's not going to affect it. So this is just an example of how simple the code can be for the users. And this is the GUI plugin that is running. It's a little bit more involved. I couldn't fit everything in one slide. I commented some stuff out. But it's basically the plugin that I'm running to control the keys and move the camera from one slide to the other. So in the same way we register, but this time it's a GUI plugin. And in the constructor, I initialize some cute element, which is just this tiny box here with the number of slides where we are. You can, usually in a normal application, you would like put buttons to control your robot, to teleoperate. You would you can plot, you can do whatever you want. Then we override the load method. And here we just receive the SDF pointer. There is no other pointer involved in GUI. You can get everything from, like the main window, for example, you can get it with a global function if you want. Then we go through, I commented out some code just left here that you're taking again the poses from this SDF. So you're making a list of all the key points for the camera that you want. And I just said that all in the XML file. We also keep a pointer to the camera. So you can see here that I use the global function to just get that. So that's the user camera. And then here I just create a callback on key press. So every time you press the key, the camera, it's going to call this. And then we check which key it was. And then we're also keeping track of an index of which slide we're at. And just move the camera to that position. So it's quite simple. And just to finalize, I want to show you the load for the system plugin, which is the really powerful one. And you can see that you can have access directly to the command line arguments before Gazebo. And yeah, that's pretty much it. Thank you for your attention. If you want to get involved, there's a bunch of links there. And we're open to questions.
The question was, what is our source of funding? Thanks for asking. So we're mostly funded by grants and contracts. So we get a lot of funding from DARPA, NSF, NASA, government organizations. We also have some contracts with larger companies like Google, Bosch, Qualcomm. Yeah. And we do take donations, but that's not a large source of our funding.
So do people actually make video games of this
I wish.
Well, you could totally do it. We sometimes make some demos. Like a few months ago for the DARPA Robotics Challenge Finals, we made a demo where you can use the Oculus Rift and some like controllers, kind of like the Wiimote, they're called the Razer Hydra, to play foosball inside Gazebo. So you had two people playing against each other. So you could definitely do something like this. Like I said, the graphics are not really competitive, and in video games you usually don't want really real physics, but you can do it. Yeah. No other questions? Cool.
Is there any consideration somebody accidentally or intentionally connect to a robot and be like, ooh, over there?
Great question. Yeah, ROS is not very well secured. I'll be honest with you. It is another goal for ROS too, to like add an encryption layer for messages, like a user interface for encryption. But it's very easy if you're on a network to search for, the IP address of the robot, like sniff some packets. The standard port for ROS communications is like everyone uses the same port, so it's all very open. Yeah. And we like to, emphasize to people that open source doesn't necessarily mean insecure. In fact, many high security, like many of the great security libraries, like SSL, are open source, and I think that's an advantage to these projects. But ROS is not an example of like a super high security project.
Yes.
I guess as a follow-up, does DDS support anything like that? If that technology had support for it, it would just be taken care of, so to speak.
Yeah, I think it's not a built-in part of the spec, but there are some vendors who build like secure DDS, and it's usually a layer right on top. Yeah.
I'm just playing, sorry.
There's a demo.
Any other questions?
He used a community edition of what's like DDS a while back, and it did not support 4-bit. We have no community edition now runs 4-bit. It would install and compile some for it, like messages.
Yeah, I believe so. There's actually a funny problem we ran into with RTI Connects, where their old version didn't support messages with arrays larger than 255, which was a really big limitation when I was trying to do stress testing. But they've improved that now as well, actually. But yeah, that's about a completely different vendor.
Or is there any other features that you hear about being talked to for the future C++ that would help?
Yeah, standard functional helped us a lot. We do a lot with passing callback pointers, and creating lambdas is really nice for user code. Although one of my coworkers says like lambdas are horrible for testing. If you want to unit test something that you make in a lambda, like you can't. So, or it's not a great interface. But I'm a big fan of that. One feature that I would really like to see is more support for real time. Now that I have had some experience with that, a lot of structures in the standard library are not great for real time, low latency, lock-free performance. But luckily, there's an SG for that. Nice.
It would seem like real time would be a challenge for the students.
In Gazebo.
Yeah.
Yes.
Yes. Actually, so real-time factor in Gazebo means something different. This says real-time factor, for those of you who can't see. And if you have a real-time factor of 1, it means the physics clock is synced up with like the real-world clock. Like your physics is running as fast as real life is. And right now, the real-time factor is like 0.9-ish. So
My computer is not very.
yeah, if you're running this on a beefy desktop, this world would probably be 1.
Simulation, as long as you don't want it to run in real time for you, you can run the simulation, leave it there for
Really
12
slow.
hours and then come back and see the results. So usually it's not such a big concern, but.
You were talking about the memory allocation problem in the real time in ROS, and you created this little virtual base class for memory allocation. Have you looked at the polymorphic memory resources in the fundamental technical specification? It's really designed for exactly what we're doing.
Oh, no, I actually haven't. If you can email me later with more information about that, that'd be great. Any other questions? Cool. Thank you very much.